Hi, and welcome back to Codex. Our talks this summer feature graduate students and postdocs who were nominated to speak by their senior colleagues. Today, we have Keenan Eikenberry, who is a doctoral student at Arizona State University. We are happy to have him here today to tell us about Markov kernels valued in Wasserstein spaces. Take it away, Mitchell. Sorry, Keenan, my bad.
Thank you. Thank you, everyone, for coming, and thank you to the organizers for giving me the opportunity to speak. Yeah, so today I'm going to talk about Markov kernels valued in Wasserstein spaces. And to motivate things, I'd just like to briefly compare function approximation to distribution approximation. So function approximation, schematically, we have something like the following. We're given input-output pairs, and we want to find some function f in a space of functions that fits that data. And as we all know, there's lots of different ways you might represent or approximate f. There's approaches coming from harmonic analysis, kernel methods, Gaussian processes, neural networks, so on and so forth. And just one thing to point out here is that the problem statements for function approximation tasks are all fairly uniform, and the different approaches tend to complement each other. Now, we can contrast this with the task of approximating distributions. And by distribution, I just mean probability measures. So here, problems and methods are seemingly less unified, at least at first glance. So problems I'm thinking about include, say, parameter estimation. Maybe you have a PDE, some basic heat equation, and you don't know what that alpha is, so you're trying to find a probable value of it from data. And so you do some kind of Monte Carlo simulation, say. Alternatively, maybe you're trying to fit a parametric statistical model. So you might have a mixture model, and maybe you're going to do maximum likelihood estimation or Bayesian methods to try to find a density function here. Now, something that may at first glance seem rather different is probabilistic programming languages. So these are getting a lot of attention these days, where distributions are essentially data structures in your program, and models, statistical models, are actually programs that manipulate these distributions. And so here's a code snippet from the probabilistic programming language that's implemented in Julia. And this seems like at first glance, well, how could this have anything to do with the others? And a final example here, what about, say, painting approximation? Here, I'm alluding to image generators, which are, of course, very popular these days. And the relevance here is that, in essence, generative models are learning distributions. So, for example, maybe you take the Mona Lisa and a bunch of other paintings and use them as training data. And you're thinking of these as possible images in a larger space of images, and you want to put a distribution on that space. And why do you want to put a distribution on it? Well, because if you have a distribution, you can sample from it, possibly conditioned on a natural language prompt, and then you can get something new. So, for example, Mona Lisa with a large conspicuous mustache. This is a prompt to DALL-E. And just to clarify, this is the original one here. This is the replica, just to be clear. So anyway, these are four highly, seemingly very different problems. You have parametric models, you have parameter estimation, probabilistic programming, generative models. What do they have to do with one another? Sure, distributions show up, but could there be some common abstract framework here that allows us to analyze these problems? Well, obviously, we're not going to capture all of the nuances and all of the specifics, but still we might ask, well, maybe these distribution approximation tasks have something in common. And we might also ask, can we retain the flavor of function approximation when dealing with distributions? And so one possibility here is that you might just decide to study distribution valued functions. So instead of deterministic functions going from some space x to y, you can consider functions going from x into spaces of probability measures on some space y. So, for example, instead of f of x being a real number here, maybe f of x is some normal distribution with mean lowercase f of x, where lowercase f here is just some ordinary function. Now, that is essentially what's called a Markov kernel, and these are very well studied. But we want to go a little bit further here, and we don't want to work in a purely measure theoretic setting. We'd like to also be able to answer quantitative questions and to connect these objects with more kind of classical questions of statistical inference like convergence and whatnot. So the idea is we should sure study distribution valued functions, but let's put metrics on everything, on x, on p of y, and on the space of these things in order to be able to do quantitative results. And so if you put those things together, our answer, as one thing that you get here, and one thing that's worth studying, is Markov kernels valued in Wasserstein spaces, or Markov-Wasserstein kernels for short. And if you look at the collection of all of those things, given spaces x and p of y, well, then the idea is that this is going to become some sort of generalized distribution valued LP space. And our claim is that Markov-Wasserstein kernels are convenient objects for studying distribution approximation problems that come up in Bayesian inference, generative modeling, probabilistic programming, and various other fields. And a feature of them is that you can study both structural and quantitative questions here. So probably the biggest outlier in the previous examples is this probabilistic programming stuff. How could that have anything to do with this? Well, I'm not really going to say too much about that side of the story for today's talk. Basically, the connection is that these objects have nice categorical properties. They assemble into what's called a probability monad. And when you study the semantics of probabilistic programming languages, these measure theoretic Markov kernels come up all the time. And so this is well-known stuff, but the difference here, kind of the new part of this story, is that we're moving away from purely measure theoretic objects, and we're trying to frame, put metrics on everything so that now we can kind of also simultaneously talk about things like classical statistical models, but also these like highly non-parametric models at the same time in kind of a unified framework. So a little more specifically, what I'm going to talk about today then is, well, we're going to be, our main object, right, is these Markov kernels valued in Wasserstein spaces. So I'll first try to just tell you a little bit more precisely what these two objects are. And then I'm going to show you that, in fact, you can integrate these things. So we develop a Lebesgue type integral for these objects, which we call the Markov-Lebesgue integral. And this gives us a nice new conceptual interpretation of what the disintegration theorem is. So the disintegration theorem is well known, but ordinarily you use iterated integrals to define this object, which we'll get to. But now we're going to show that, oh, actually, you can think of this in the context of a larger integration theory for these things. And as far as applications go, I'm not, as mentioned, I'm not going to go into the probabilistic programming or generative modeling ideas too much. Instead, I'm just going to try to show you how you can reconstruct Bayesian inference in this setting, how you can get, in particular, precise definitions of Bayesian inverse maps, and how you can get a generalized Bayes' law in this setting. So let's jump into it then. We need to say what these Wasserstein spaces are and what Markov kernels are. So just a background assumption, we're always going to be working with Polish metric spaces. So everything in sight is complete and separable, and we're always going to work with Borel sigma algebras. Now, what we want to do is we want to put a metric on some space of probability measures, but we actually need a regularity condition. So we don't need to worry about the details of this thing. Basically, just a Borel probability measure on some measure space has finite pth moment if, roughly speaking, the expected distance between any 2 points in the support is finite. And so let's restrict to that collection so that we have a little bit more regularity to work with. We'll call that P sub P of X. This is the thing, one of the things that we want to put a metric on. And the way we're going to do it is that we're going to appeal to optimal transport. So here's another DALL-E image. This essentially is optimal transport in a picture. And what do I mean by this? Well, one way to think about optimal transport is that it's about figuring out the most efficient way of rearranging one probability measure into another. And so if you think of your first probability measure as a big pile of dirt, and if you think of your second probability measure as, well, the opposite of a pile of dirt, let's call it a hole, then optimal transport is asking, what's the most efficient way of taking this pile of dirt and filling in this hole over here? So that means you need two things. You need to first say, what does it mean to rearrange one measure into another? And then you need to say, well, what does it mean to do so efficiently? So the answer to the first question is that you use what are called couplings. So a coupling between probability measures mu and nu is this going to be a joint distribution. so just some probability measure on x cross y, such that its first and second marginals are given by mu and nu respectively. And that just means that this following equation here holds for any elements of your sigma algebras. Now, the intuition for a coupling, why does this tell you how to rearrange one mass into another? The intuition is that a coupling is a relaxation of a transport map. And so to go back to our image of dirt, a transport map is a deterministic way of taking your pile of dirt and filling in the hole. So you would say, I'm going to take this grain of dirt and put it exactly in this location, this grain of dirt and put it exactly in this location, so on and so forth. So you have a measurable map on your underlying spaces, x to y, and you want the push forward of your initial measure to equal the target measure. And what this means, of course, is that, well, it's the sort of the usual push forward. What's the mass assigned to be? Well, you pull that mass back with your map t and measure it with mu. Now, in a picture, the connection is as follows. So don't worry about the epsilons. This has to do with an entropic regularization algorithm. I just want to compare the epsilon equals 10 frame versus the epsilon equals 1 frame. So if you imagine that there are one-dimensional probability distributions on the x-axis here and on the y-axis here, then in the epsilon equals 1 frame, this is very close to a transport map, right? Because it's close to an actual graph of a function. And it's saying, take the mass that is in this x slice and put it exactly in this y location. Now, if you relax that, if instead of deterministically putting your dirt into the hole, you say, well, I'm going to grab a scoop of dirt and I'm just kind of evenly spread it across these y locations, you get something that looks increasingly like the epsilon equals 10 frame, where now the mass in this x slice is distributed over a larger portion of y locations. So that's the difference between couplings and transport maps. And the reason you use couplings is because you end up with a far nicer optimization problem. So that's what it means to rearrange mu into nu. We're going to use the notion of coupling. But now, in order to put a metric on these spaces of probability measures, we're going to use the notion of, well, we want to take the coupling with the lowest cost. So there's a lot to digest here. Basically, what's going on here, this is what's called the Wasserstein metric. And the setup is that if you give me any Polish metric space in the world, x dx, and here we're going to call dx the ground metric, then you can define the Wasserstein metric of order p on the space of Borel probability measures over that ground space x. And it's defined with this integral here. So don't worry about the pth root here. Let's just look at the integral. What this integral is saying is that this capital pi here, pi of mu comma nu, this is all couplings between mu and nu. And now your ground metric dx, you're going to take the pth power of that, and you're going to regard that as a cost function. And the intuition is that you are trying to rearrange mu into nu using the coupling pi that has the lowest cost. So this integral, if you take a coupling that tells you how to rearrange things, well, then if you integrate your cost against that joint distribution, against that coupling, that's assigning some quantity to that rearrangement, right? Obviously, it's more efficient to take this dirt that's in this lower corner and assign it to the corresponding lower corner, as opposed to, moving dirt long distances. And so you say, all right, for any coupling, we can quantify the effort that it takes to rearrange the mass, one mass into another. And we're just going to take we're just going to do the one with the least amount, that costs the least amount. So you're going to take the infimum over all of these couplings. And in fact, the infimum is achieved. And so this gives you a metric on your space of Borel probability measures over x, and subject to this regularity condition. So so pretty much for the Wasserstein space stuff, we really only need the definition here, that we want to know what the Wasserstein metric is, and then we want to know just some basic fundamental properties of these objects. First off, there's this lifting property, which is that this ground metric is preserved via embedding your original space into the Wasserstein space with Dirac masses. And this theorem, this is, I think, really extraordinary. If you start with any complete separable metric space and you construct the Wasserstein space, so this is going to be the Borel probability measures on X with this regularity condition, and you're going to equip it with this metric here that we just defined. That itself is also a complete inseparable metric space. And so this, as just a quick side note, this is one of the reasons why these objects, why there's like a nice categorical theory going on here in the background, is that this is related to what's called a probability monad, where you take in your metric space and you still get an object of this category of metric spaces. And in fact, you can iterate this, right? The Wasserstein space is a complete inseparable metric space. So therefore, you could take the Wasserstein space of the Wasserstein space, right? And you can study distributions of distributions. This actually turns out to be useful, but we're not going to go into that really for this talk. Basically, all we need to know is the definition. So this is a Wasserstein space. And now we want to study maps going into Wasserstein spaces. So we can now talk about Markov kernels a little more precisely. So if you go to Wikipedia and look up Markov kernel, this is the definition you see, and this is the definition you see in lots of papers, where a Markov kernel from a measurable space X to Y is a map of this following form, where you define it from the sigma algebra on Y cross X into 0, 1, and it satisfies these properties. So let's not get hung up on it. Basically, it's like an X-indexed collection of probability measures with this measurability condition, but this isn't the best way to present it. Like this, you have to check these two conditions. The more intuitive definition is that a Markov kernel is literally just a measurable map from X into P of Y. Well, but that means you have to turn P of Y into a measure space, and the way you do that is you equip it with the initial sigma algebra with respect to all evaluation maps, where the evaluation maps are defined as seen here. And this is for any B in your sigma algebra. Now, to show that this definition is equivalent to this definition, this is very straightforward for the measure theoretic case. But again, we want to move beyond measure theory and work with metric spaces, metric measure spaces, be able to actually quantify things. And so what we would like to do is we would like to view Markov kernels as Wasserstein valued Borel maps. So F is going to go from some complete metric space or some Polish metric space X into some Wasserstein space, P sub P of Y here. Now further, we'd like to study the collection of all of these things. And in general, you can define these LP spaces for any complete inseparable metric spaces X and Y. So LP sub mu of X, Y here, this is just going to be all nice measurable functions equipped with the LP metric, where the LP metric is given here. It's just this sort of pointwise integral trying to quantify distance here between these functions F and G. So for our case, well, again, right, P sub P of Y is a Polish metric space. We have a metric on it. So our metric will be as pictured on the bottom line there, right? That we're just going to use the Wasserstein metric. Now, obviously, you could just declare that these are the objects that you're interested in, but we wanted to actually show that this perspective of things is equivalent to this kind of more common definition. And in our case, this actually takes a decent amount of work. In the purely measure theoretic case, like it's just a couple lines. Here, it took a little bit of work to show that if you work with this kind of ordinary definition of a Markov kernel, well, it turns out that you can define a Wasserstein type metric for that object. Let's call that MW sub P. So this comes from a recent paper by Patterson. And it looks very similar to the ordinary Wasserstein metric. You use this generalized notion of couplings. But it's kind of complicated, right? I mean, you have the more tedious definition of Markov kernel, and then you have this fairly elaborate definition of the metric. So we would like to work with just this generalized LP space picture of things. And in fact, you can show that these perspectives are equivalent. So those are the objects that we're interested in. And again, we're claiming that these are like these generalized LP spaces, these distribution valued LP spaces. Well, so if they're worthy of the name, surely there should be an integration theory here, right? And in fact, there is. So generalized integration is typically defined for functions valued in Banach spaces, right? There's like the Bachner integral among other variants. And fundamentally, you're exploiting the linear structure in your target space. Well, as long as you're only integrating against a probability measure, you can, instead of thinking of linear combinations in your target space, you can instead think of convex combinations. And in fact, you can think of like infinite convex combinations of things in your target space. And you can use that as a substitute for having a Banach space structure. So that's what we do here. And we can develop an analog of Lebesgue integration for these objects. So obviously, we're going to have to start with simple building blocks. So a Markov kernel, we call it countably simple if it's of the following form. You just take a pairwise disjoint partition of X, and then for each of those patches of X, you just say that your Markov kernel is constant there. You say that, well, we'll assume it's just this single nu J probability measure there. Now, one thing also to note is that for our basic building blocks here, we're going to allow them to be countable as opposed to just finite. So the reason we can get away with this is because we're only integrating against probability measures. And so, for example, when you define the integral for a simple Markov kernel, well, it's exactly what you would think it is, right? That if you integrate a simple Markov kernel against a probability measure, well, then it's going to be a probability measure on Y defined as seen here. And since everything is a probability measure, everything's absolutely summable. And so when you check that this thing is indeed a measure, everything works out by absolute summability. And so that's how you can get away with using countable simple building blocks instead of finite. And it turns out that that makes the extension to general Markov kernels much nicer. So we'll see how that works in just a second, but we need one more notion, right? Ordinarily, the most common way that the Lebesgue integral is developed is that you take a supremum over simple functions, right? Well, what would a supremum over these Markov kernels be? It's not exactly obvious. Well, in Bogachev, so there's he has this 2-volume epic tome on measure theory volume 1 and 2. He defines the notion of fundamental in the mean, and this is a definition that it gives you a Lebesgue integral that's equivalent to the supremum over simple functions, but also it's a definition that we can more easily replicate in our setting. And so an analog of this fundamental in the mean condition that Bogachev develops is as follows. So we're going to say that a sequence of Markov kernels is weakly Cauchy if the following condition holds. And essentially, if you look at this, what it's saying is that, well, basically these things are getting close in the LP metric. And when you have that notion by itself, together with these countable simple building blocks, is enough to guarantee the following: that for any Markov Wasserstein kernel F, you can find a sequence of countably simple Markov kernels that converge uniformly to F in the Wasserstein metric, and also these things are going to be weakly Cauchy in the LP metric. So then, this is the fundamental approximation result that allows you to define integration for these objects in general, because weakly Cauchy implies that your sequence of probability measures defined via that initial simple definition of the integral, that is going to be a Cauchy sequence in the Wasserstein space. And then, as we already noted, right, the Wasserstein space is complete, so we get a limit and we get uniqueness from uniform convergence. And so then also, the fact that you can use countably simple Markov kernels as your basic building blocks instead of finite Markov kernels, that is what allows you to get uniform convergence instead of pointwise convergence. So you have no need, since we're only integrating against probability measures, you don't need some kind of analog of like an Egorov theorem here. So that's the fundamental approximation result, and that allows you to extend to a general definition of integral, general integrals for these Markov kernels. And one thing to note is that ordinarily, when people work with Markov kernels, ordinarily the way you define an integral of a Markov kernel is that you define it via an iterated integral. So if you want to say what is some probability measure on y that you can integrate this f into, given some probability measure mu on the target space, well, ordinarily you would define that via test functions. So on the right-hand side, you see the measure that you get on y defined via iterated integration, right? You take test functions in just continuous test functions, and you define a functional. Well, it turns out that the probability measure that you get from defining this functional is exactly the same as the probability measure you get from this definition of the Markov-Lebesgue integral, which is good, right? If that weren't the case, it would have been a terrible theory of integration. So this is good news, right? That ordinarily people work only with iterated integrals when working with these objects, but in fact, you can get an actual theory of integration for them. And another thing to consider here is as follows. So I mentioned disintegration earlier. And so what's disintegration? Well, we defined integration. So let's think of disintegration as a way of undoing integration, hence the name. But how does that work? Well, let's think about this integral here that we just defined in a following special case. Suppose you take a Markov kernel f, and suppose instead of integrating it into a probability measure on y, what if you instead integrate it into a joint probability measure? And the way we're going to do that is that we're going to consider the following Markov-Wasserstein kernel. Instead of just taking f of x, which is a probability measure on y, let's tensor that with the Dirac mass at x. And so here, the tensor notation, this is just the usual product measure here. So as seen on the second line here, right, just that the value of this thing on a rectangle, it's just the multiple of the two measures. And notation-wise, it's easy. You tend to go back and forth between the conditional notation versus function notation versus this subscript notation. They all just mean the same thing. But in any case, if you consider Markov-Wasserstein kernels of this form, right, well then that means you have a Markov kernel going from x into p sub p of x cross y. And so therefore you can integrate it into a joint distribution using exactly the theory we just did. So why is this interesting? This seems like a rather restricted thing, right? To take Markov kernels tensored with Dirac masses. That seems rather restrictive. Well, in fact, it's not. You can reverse this process for any joint distribution. So if you start with any joint probability distribution gamma, you can actually find almost surely unique Markov kernels, f and g, one going from x into p sub p of y, one going from y into p sub p of x. And in fact, you can reconstruct that joint distribution as a Markov-Lebesgue integral. Now, ordinarily, this disintegration theorem, this is usually just defined with the iterated integrals. So you would define it via the functional definition. But in fact, this is now a literal equality, and it shows us that given any joint distribution, you can reconstruct that joint distribution with these Markov kernels tensored with Dirac masses. So this seemingly restricted form actually turned out to be much more general than it seems. And so why do we want to talk about disintegrations? Well, first off, let me just give you a kind of basic justification for why disintegrations are interesting. Let's suppose that x and y are just r. And so let's suppose our joint distribution is, say, a square on r cross r. Well, when you first learn about the Lebesgue integral, it sometimes seems a bit unsatisfying to learn that a one-dimensional slice of that square actually has Lebesgue measure 0. And when you first hear about this, you may say to yourself, well, that seems weird because I thought calculus said that, the two-dimensional object is glued together but as a bunch of one-dimensional objects. And so a disintegration is exactly trying to capture that intuition in a precise measure theoretic setting. So if gamma here is just a square in R2, well then the disintegration theorem is saying that you can view that gamma, that square, as either an x-indexed collection of probability measures on y, or a y-indexed collection of probability measures on X. So in other words, it's just saying there's two different ways to slice that square. There's either horizontal lines and vertical lines, and that in fact, they do precisely glue together into a joint distribution. So that's the intuition in general for disintegrations and why they're interesting. But in fact, this right here is going to be how we reconstruct Bayesian inference in this setting. So remember this slide because something very similar is going to come back. But the difference is that instead of calling that Markov kernel going from y to x, g, we're going to call it a Bayesian inverse. And instead of calling nu, we're gonna have some different notation from it. But basically, this slide right here is the secret to a precise definition of what a Bayesian inverse map is. And so that's really why we're interested in them. So with that, let's try to be a bit more precise about what I'm saying here. So we have our objects, we have Markov Wasserstein kernels, we can integrate them and we can disintegrate them. So we have this theory of these generalized LP valued, or sorry, these distribution valued LP spaces. What can we do with them? Well, one thing that we can do with them is that we can study Bayesian inference in this setting. And so let's start with just the discrete case. Suppose you have a discrete parameter space X and a discrete space of data Y. Now, ordinarily, Bayes' law is written something like the following. You observe some piece of data Y, and you want to put a new distribution. You want to define the posterior distribution on your parameter space. You're saying, oh, well, what's the most likely parameter now for our model, given that we've seen this piece of data Y? And so often you usually just, everything is just P, right? The probability of X, given that you've seen Y, is the probability of Y given X times the probability of X over probability of Y, right? This usual kind of thing, or just in set theoretic notation, as everyone has seen, right? Just probability of A given B is probability of B given A times probability of A over probability of B, right? And this just follows from the definition. So, but this notation is very overloaded, right? And it's worth being a little bit more careful here about what's actually going on. So let's try to spell out what all the objects are in this case. So for the finite case, the prior is just going to be an element of a probability simplex, right? It's just a vector of positive real numbers that sum up to 1. And let's not call everything P. Let's be clear about the different objects here. Let's call it mu. And now the forward model, or the likelihood, so if you assume that X is the parameter and you're saying, well, what's the probability that Y is the true distribution? Well, you can model that as a Markov kernel, right? You can say that the forward model, or the likelihood, is just a Markov kernel going from X into P of Y. And in the discrete case, each f of j, so for any parameter j, the Markov kernel here, well, it's just going to be a discrete distribution on Y. So it's just going to be another vector of numbers, now an n-dimensional vector of real numbers that sum to 1. And if you like, you can summarize all of that in a matrix, right? And now you need one more thing in order to, then define the Bayesian inverse. You need the marginal likelihood. So this is just a distribution on Y given as follows. This is just saying, this is our best guess given f and given a prior mu. This is our best guess of what the true distribution actually is on Y. And it's just defined as this, normalized sum, right? You say, you go through all possible parameters and you weight those different estimates by their prior probability, sum all those up. So with those three things, you can now define a Bayesian inverse precisely using those three objects, right? So if you have this forward model F and you have the prior mu, you can say that the Bayesian inverse, which we denote F dagger sub mu, the Bayesian inverse is a Markov kernel going the other way. It's a Markov kernel going from Y into probability distributions on X, and it's given as follows. Just basically exactly what we just saw, right? That to know the new posterior distribution, you flip things around and you write that in terms of your forward model, the prior, and the marginal likelihood. So in other words, we go from this undifferentiated case where everything is just P to now a little bit more precisely, we realize that, oh, right, okay, there's 4 different objects going on here. And now, in order to connect this up to everything we've just been talking about, how do we recover Bayesian inverse maps? And also, what's the relevance of the disintegration theorem? How does that come in? Well, I mean, probably it's already somewhat obvious, with this Markov kernel formulation, but let's be explicit about it. And the way to make this precise is to observe the following. I labeled this non-symmetric Bayes' law, right? And this is the way you typically see Bayes' law, is that it is a rule for arriving at a posterior distribution. However, what if you multiply this normalizing constant over to the other side? Well, then, instead of thinking about Bayes' law as a way of arriving at a posterior distribution, one way to think about Bayes' law is in the symmetric form. You can say that Bayes' law is actually saying that there's an equality between these 2 joint distributions, or it's just 2 different ways of writing this joint distribution, right? That instead of saying, okay, I have a parameter space and I have a data space, and I want to update that parameter, the distribution on the parameter space. Instead, you can think that you have a joint distribution on X cross Y, on parameter space cross data space. And now the Bayesian inverse is exactly the thing that makes this joint probability distribution, that balances this equation, right? And so this final line here, when you write this equality of joint distributions with more precise notation, this is starting to look very close to the disintegration theorem with only 2 differences of notation. So, right, this if you look at the discrete version of it, right, that you just have f and mu, well, basically if you just integrate those things, you get now the precise measure theoretic version of what the Bayesian inverse map is. So given any Markov kernel, f, any Markov Wasserstein kernel, f from x into y, and given some prior on x, the Bayesian inverse of f with respect to mu is going to be this Markov kernel going the other way that satisfies exactly the equation that we saw in the disintegration theorem, right? It's this equality of joint distributions. And so here, this f dagger sub mu, this is what was g before, and then f o dot mu, this is just our notation for the second marginal of the joint distribution. And in this case, instead of it being a sum, well, it's this integral, right? You can say that the marginal likelihood is this joint distribution, or sorry, this probability distribution on y, and it's your best guess of what the true distribution is given your model f and given your prior mu. Actually, so you can define it just as seen there as this integral, but actually in the background, the categorical framework is kind of lurking here, where you're thinking of this as actually being a composition of a push forward operation that takes you into the iterated Wasserstein space, and then an averaging operation. And all of these maps behave nicely with respect to categorical properties. But again, that's not going to be the focus here. We're just gonna consider the more kind of quantitative aspects. And that is what I'd like to try to sketch out a little bit next is, well, everything I've been saying here, this Markov kernel formulation of Bayesian inverse, and trying to be explicit, let's not call everything P, let's note that there's actually 4 different objects going on here. All of this is pretty well known in probabilistic programming semantics, right? That if you're going to teach your computer how to do Bayesian inference, you have to be explicit about these things. Things need to type check, and you can't just call everything P anymore. So that's this is a well-known picture of things. So what's new in our setting? What are we adding to this? Well, the new thing now, right, is that in our setting, prior, forward, model, marginal likelihood, and inverse map, all of these things live inside spaces equipped with these transport type metrics. And so now we can start to gain quantitative control over this. We can have, instead of just measure theoretic ideas, instead of just structural ideas, we can actually connect up with like convergence ideas and rates of convergence, say. And so first, though, let me say that in order to define the Bayesian inverse map, you define it in the symmetric form, well, that leads that leads to the question, right? Okay, if you define the Bayesian inverse map using the symmetric form, what's the non-symmetric form? And so let's take a look at that real quick. That you do in fact have a generalized Bayes' law in the setting of the more ordinary type, where it's giving you a rule for how to write the posterior distribution. And so that looks like the following, that if you have a prior mu naught, you can define this iterated update, right? Where you say, okay, I'm going to observe a data point y1, and I'm going to use the Markov kernel that I get from the disintegration theorem to now get some new posterior distribution mu1. And you can do that over and over, right? You can do these iterated updates upon observing data points y1 through yn. And in fact, it turns out that this iterated sequential update is equivalent to taking n many copies of your forward map and just updating all at once, as if on a quote unquote single data point, where the single data point is now this n-dimensional data point, right? So this iterated update, where you sequentially, iteratively update, turns out to be the same as just updating all at once with n copies of your map. And you get to recover an ordinary Bayes' law with this formula here. So don't worry about the limit with respect to s. This shows up for non-interesting technical reasons. Let's just look at the integral, this ratio of integrals itself. If you stare at it, well, and if you think that n equals 1, for example, then this is basically exactly recovering the ordinary Bayes' law in the discrete case. So to try to give you a little bit more intuition here, first, let me just say that this generalized Bayes' law, this also shows up in a paper by Yost et al. But here we can give a nice simplified proof using the approximation machinery. And we also get this relationship between this iterated update versus the all-at-once update with n copies of your forward map. And the intuition is basically just something like this, that if you apply this, this approximation machine that we developed using the for the Markov-Lebesgue integral, then this continuous object and this, maybe it looks a little bit confusing about, well, what's the intuition for this? If you just approximate this thing with these simple Markov kernels, then it turns into the discrete case, right? Because let's just suppose you're observing one place of data. And now let's suppose that your Markov kernel, maybe you're just going to approximate it as a simple Markov kernel with 3 different parts. Let's say that over the patch E1, your Markov kernel is just the constant value nu1. Let's say that over E2, the Markov kernel is nu2. Over E3, it's nu3. And so if you want to know how much mass you should assign to E1 after observing the data point y1, well, then basically you should just do the ordinary Bayes' law, right? You should say, all right, well, what's the likelihood of observing y1 given that nu1 is the true measure? Let's weight that by our prior confidence that nu1 is the true distribution, and then let's divide by the normalizing constant. And so this approximation machine that we developed for the Markov-Lebesgue integral transforms this continuous setting into the discrete setting. And now the way you go from this 1-point update to the general endpoint update is by proving that initial formula on the top line, by saying that this iterated update is actually just n many copies of the forward map updated all at once. And so, yeah, that's something like, again, as mentioned, this generalized Bayes' law shows up elsewhere, but you can really simplify it and get a lot more intuition for what's going on by using these ideas that we developed for the Markov-Lebesgue integral. And so now, let me just say, that the big thing that we've really been working on, this has been like 5-6 months of hard work to try to actually prove that this Bayes' law converges. And we're about, I don't know, 95% of the way there. I couldn't in good conscience label it a theorem, but I would say that you can bet on this. So the idea is that if you have a sufficiently nice Markov kernel, you need a few additional regularity conditions. Well, then you can get convergence at least in the following settings. If your true distribution tau is in the image of your model, and if you have this condition on the supports, so if the support of your true distribution is contained in the supports of fx for all x in the support of your prior, then this Bayesian update, where you either update sequentially or you update all at once, this process is going to converge to some optimal mu star in the Wasserstein metric. So in other words, you're going to arrive at some mu star such that when, the image of that thing under F, if you look at the marginal likelihood, you actually you recover the true distribution, and you're converging in the Wasserstein metric. And so that is basically the the current state of where we're at with this theory. And what we'd really like to do is now to start trying to leverage these convergence results finish getting this convergence result in place so that we can try to get onto some of these other applied topics like the generative modeling applications, for example. And a crucial question to think of here when you're actually trying to extract insights from these ideas, from this idea here, is this condition that tau be in the image of your model. That's something that you have to think about for algorithmic applications. How might you relax that assumption, or how might you be confident that your model F is going to capture the true distribution? And then you have the support condition. So to sketch out some of the ideas we want to talk where we're trying to go with this now, that we kind of have the foundations in place, or most of the foundations, I'll just say, first off, this setting, since we have metrics on everything, it's a really nice, convenient setting for talking about approximate Bayesian inverse maps. And in our setting, you can just say that an approximate Bayesian inverse map is any G, any Markov kernel G that's close to the actual Bayesian inverse map in the LP metric, right? And so similarly, you can consider surrogate models for your forward map F. So this is one direction to go in. What happens when you try to deal with approximate maps instead of exact maps? You can also consider stability questions. Is inference stable under perturbations of the prior, target, and forward distributions? You have metrics on all these things, so you can ask these questions. And one direction where we're really interested in is trying to think about these generative models in a more abstract way. So for example, abstractly at least, you can think of a generative adversarial network as a Markov kernel, or at least this generator, right, is a Markov kernel. So you can think of, let's skip down to the second line just to try to spell things out a little more plainly. So this theta G, this is a parameter space, and F is taking you into some space of functions, right? So this is basically your neural net. You're saying, all right, we want to find some function F parameterized by some space theta G, and you have some latent distribution mu Z, some fixed latent distribution mu Z that you're trying to push forward in order to arbitrarily approximate some target distribution on a space X. And then what you do is you tack on a loss function to that, right, in order to try to optimize things. And the discriminator, well, you can either think of it as being a deterministic Markov kernel, or you can actually just say there's this interesting perspective by Chu et al. In a fairly recent paper, where you can kind of just think of generators as being the fundamental objects, and discriminators arise via a more kind of fundamental convex conjugate duality. And so you can kind of say, well, at least as far as like the abstract picture of things goes, the interesting thing is just to study these Markov kernels. And also you can think about like diffusion models and autoencoders in a Markov kernel framework. And more abstractly, just to kind of encompass these different pictures, an interesting, one of the main directions we're trying to look at here is to just think of these high-dimensional Markov Wasserstein kernels and also priors or hyperpriors, and to study universal approximation guarantees. So we have close to our first convergent result here, well, we'd now like to try to take things in a more computationally grounded direction. How can we get good computational representations of these objects? And how can we make things even more quantitative? How can we move from just convergence to, say, convergence rates, for example? And so to sum up, we've laid the foundations of this theory. We have our isometric isomorphism result telling us that these two perspectives on Markov kernels are the same. We can integrate these objects, which leads to a nice new interpretation of the disintegration theorem. There's this whole second story that can be told about Kantorovich monads, that you get monads for Wasserstein metrics of any order. So the case of p = 1 is well known, but here we expand that to the general case. We have a generalized Bayes' law, and then we're also pretty close on convergence here. So we have a good foundation to work with and a lot of future directions to go in. So also just briefly flash references here so that if you're watching this online, you can pause the recording and take a look at some related papers. All right, thank you.
All right, let's smash that reaction button.